we are now ready to venture toward boundary value problems. In boundary value problems, we deal with ordinary differential equations such as y double prime equals a function of x, y, y prime in certain interval a to b. Here at x equal to a, the value of y is given, that is our one boundary condition, and then at x equal to b, the value of y is given, that is the second boundary condition. Since in our differential equation we have y double prime, this is a second order equation, so we need two boundary conditions. These are the boundary conditions here. If instead of y at x equal to b, we know y prime at x equal to a, then it becomes an initial value problem. But we don't know y prime at x equal to a. So right now it's a boundary value problem with y double prime as a function of x, y, y prime, and the value of y at x equal to a and x equal to b are given. In particular, we will talk about shooting method in this lecture, where the basic idea is that we take a guess of y prime at x equal to a, and with that guess, this boundary value problem becomes an initial value problem. So we solve that initial value problem and find what would be the value of y at x equals b, and let us say the value is e. We know the value of y at x equal to b is given as d, but after our calculation we are getting e, which will very likely that e will not be equal to d. So what we do, based on the difference between this e and d, we update our guess initial condition y prime at x equal to a, and we keep it updating such that eventually e becomes almost equal to d, and at that point we will say that we have the solution. So this method is an iterative method, and this is something we call shooting method. So let's see that how it works. First of all, when we are talking about boundary value problems in ODE, they are always second or higher order problems. A first order problem in ODE is always initial value problem. Second order problem may be initial value or boundary value. To be boundary value, it must be second or higher order. Then only we will have boundaries. And in such problem, in boundary value problem, time does not exist. So there is no time or time-like variable here, which means that the solution has reached in some sense a steady state or equilibrium state. So let's see with some example. For instance, this equation f triple prime plus half f double prime equals 0 with the condition f equals 0, f prime equals 0 equals 0. So that means that at x equal to 0, both f and a prime are 0. And for x equal to infinity, we write that limit L tends to infinity, x equals L. So it essentially means that x equals infinity when x being very large, the f prime equals 1. So you can see that now my domain goes from x equals 0 to all the way up to x equals infinity. And I have values at both this boundary. At x equals 0 boundary, I have f0, f prime 0. And at x equals infinity boundary, I only know f prime as 1. So this is a typical boundary value problem. This particular problem is extremely important in fluid mechanics, and we'll discuss about the solution of this problem in this lecture. This is something called Glaciers equation. So if you have taken a graduate level course in fluid mechanics, then you will see that this equation comes in boundary layer flow over a flat plate. This is a very, very important equation which was developed by Prandtl and Glaciers. We'll see how to solve it numerically. You may already know that how to solve this equation analytically through a series solution. Another equation of importance is something that we are talking about. This is u double prime is a function of x, u and u prime. with at x equals 0, u equals u1, x equals L, u equals u2. This sort of equation often you will find in steady one-dimensional diffusion. So if you have taken a course in heat transfer, then in heat conduction, one-dimensional heat conduction problem, you will have such equations. This equation also see that time does not exist here. In both the boundaries x equal to 0 and x equal to L, we know the value of u1, value of u as u1 and u2. So this is a typical example of a boundary value problem. So how do you solve such problems? We already know how to solve initial value problems, but how do we solve boundary value problems then? There are usually two approaches in boundary value problem. First approach is that we take this boundary value problem and convert them to set of initial value problems. Then we iteratively update the unknown initial condition. To convert it as initial value problem, we have to take some guess of initial conditions because we don't know all the initial conditions. So we take some guess, and all those guess values we iteratively update them to generate the known boundary condition. If this is my approach 1, approach 2 is we take this boundary value problem and we don't get into this initial value problem. We directly convert this problem to a set of linear equations, means this AU equals B system, and then we solve this AU equals B system using some of the techniques that we have learned before. So the first approach is what we are going to talk in this lecture is known as shooting method. And the second approach is the approach of finite difference, or the same thing is applied in finite volume or finite element method. The second approach, the finite difference approach, is more generic in nature, and this is the approach we will continue as we go to the partial differential equation in our upcoming weeks. So let us take this example of a Glaciers problem. Here at x equal to 0, f and a prime both are equal to 0. At x equals infinity, the f prime is 1, and in between x greater than 0, I have f triple prime plus half f double prime equals 0. If you have done a course in fluid mechanics, you know this f represents stream function and a prime represents velocity within the boundary layer. Now in this problem, we see that one boundary is at infinity. Numerically, it's difficult to set anything as infinity, but we have to assume a sufficiently large value of L and we have to go by that. And this is something we have to try with different values of L to see that which one is sufficiently large. But that is a secondary issue right now. First, of course, how we are going to solve it, even if it is not infinity. So after we take this some value of L, we have to take a reasonable initial condition. We have a missing initial condition here. We are going to apply shooting method. For shooting method, I have to convert this to initial value problem. How I am going to do that? So here I have f at x equal to 0, f prime at x equal to 0. So I need to have f double prime at x equal to 0. So what I do, I take a guess of f double prime 0 as a. This a is my initial guess of the unknown initial condition. And then I solve this problem. Similarly, I take another guess, that is f double prime 0 equals b. And again I solve this problem, and then I try to see that how I can march toward this x equals infinity, f prime equals 1. So what we do is that when I solve this problem with f double prime 0 equals a, I get f prime at x equals L to be alpha. And similarly, when I solve Glaciers equation with f double prime at 0 equals b, I get f prime x equals L as beta. So I now have two values of f prime at x equals L based on the two different initial conditions that I have guessed. Now I have to select these initial conditions A and B in such a way such that this alpha and beta, one of them is less than 1, one of them is greater than 1, which means that this alpha minus 1 multiplied by beta minus 1 must be less than 0. To reach here, I may have to trial with different A's and B's. Once I reach here, I can hope that we can now go with the shooting method. And shooting method takes pretty much what we have learned in bisection method of solving nonlinear equation. So this bisection type algorithm will now apply, and we will modify this A and B until we have this f prime x equals L equal to 1. So let's see how we do so. We have started with f double prime 0 equals A, and that gives me f prime x equals L equals alpha, f double prime 0 equals B, and that gives me f prime x equals L equals beta. And here alpha minus 1 into beta minus 1 is less than 0. So if alpha is greater than 1, then beta is less than 1, or if alpha is greater than 1, then beta is less than 1. So now what we do, we set f double prime 0 as A plus B by 2. With this, once again, we solve this equation with the other initial conditions are given, and we get the f prime at x equals L equals gamma, another value. Now we have to see, we will replace either alpha or beta by this gamma, and how we are going to do that. We'll see that this gamma is greater than 1 or less than 1. If this gamma falls within this alpha and beta, then only we can move ahead, otherwise we can't do anything. If gamma is within alpha and beta, then gamma must be less than alpha, greater than beta, or greater than alpha, less than beta. In that way, gamma minus alpha minus gamma minus beta must be less than 0, and this condition has to be satisfied so that we can apply shooting method. Only then we can apply shooting method. Otherwise we may have a problem when the problem itself may be unstable, or we may have taken a completely wrong initial guess. So let us see that when my gamma is within alpha and beta, what I'll do. We want to see that this gamma falls on the alpha side or beta side. If gamma falls on the alpha side, then gamma minus 1 multiplied by alpha minus 1 is greater than 0, which means that is alpha is greater than 1, gamma is also greater than 1. In that case, we'll replace this alpha by gamma. Also, if gamma less than 1 and alpha less than 1, then again gamma minus 1 into alpha minus 1 is greater than 0, and the same thing will happen, alpha will be replaced by gamma. Otherwise, if gamma and alpha are in different side of 1, then we'll replace beta with gamma. If gamma and alpha, gamma minus 1, alpha minus 1 is less than 0, then must be gamma on the size of beta, and then we'll replace beta with gamma. In short, if we have 1 here, which is the given boundary condition, alpha is here, beta is here, and after we get the gamma, we'll see that where my gamma lies. If gamma lies here, then I'll remove this alpha and I'll take this gamma for my subsequent iteration. On the other hand, if gamma lies on the other side, like here, then we'll replace beta with gamma and we'll go for subsequent iterations. This is exactly what we did in bisection method. We'll continue our iteration until our gamma comes very close to 1. That means we can set our stopping criteria as this gamma minus 1, absolute value of that must be less than some small user defined epsilon. At that point we can assume that our solution has converged, and we can look at the converse solution. So let's see how we'll do that. This is one of the case where we have this converse solution. This is f triple prime plus half f double prime equals 0, Glaciers equation. And I have three variables, f prime, f double prime I am calculating. This is my f prime. This black is my f and the blue is my f double prime. You can see that at L tends to infinity, that means in x direction if I go further and further, this red curve is coming almost 1, so at infinity this goes up to 1, but we don't know where the infinity will be set, so we have to repeat the same problem with different values of x. In this case I have tried with 10, 15, 20, 3 different values of L, and then I found that even 10 is okay, but we can, there is no point in going beyond 20. We can see that for L equals 20, this f prime becomes 1 as much less than 20. F prime becomes 1 is pretty much around x equal to 5, so much less than 20 it becomes 1, so we can safely take this 20 as our infinity and we can go with that. We'll also see that f double prime 0, which is an important quantity in fluid mechanics, will come out to be 0.332 once the solution is converged, and after that this comes in L equals 10, and as we go from L 15 to 20 there is not much of a change in f double prime, so in f20 also you will find this to be 0.332. Similarly, f prime at L, you can see that this is almost 1 here, so we can say that the solution is converged. If you have a fluid mechanics textbook, you can also match your result with series solution and you will find that it will be all right. In this case, the initial guess of f double prime 0 is taken to be 1 and 0.1. You can try with these values and you will find that you will reach here this f prime x equal to L as 1. We'll see at the end of the iteration you will have two values of, because we are using a bisection type algorithm, so we'll always have two values of f double prime 0, and you can see that both of them are close to 0.332. In this point we can say that it has converged, and as I already mentioned that the analytical solution, which is available in many fluid mechanics text through this is a series solution that was done by Dr. Glaciers in his PhD thesis. So you can check this solution from a fluid mechanics book and you can match your results with that. It should match almost exactly. So now to summarize the suiting methods, in suiting method we convert the boundary value problem to a set of initial value problems and we guess the unknown initial condition, and then we update the initial guess of the unknown initial condition, and until we have the boundary condition that matches with the given value. This is a simple yet powerful technique which is used in a wide variety of ordinary differential equation boundary value problem. You can solve a small exercise problem. Here we solve for y equals f of x within the domain of -1 to 0. Here y double prime is twice y to the power 3. At y equals -1, x equals -1, y equals 1 by 2, and x equals to 0, y equals 1 by 3. You should be able to solve this problem analytically as well, and you should be able to plot the results. So you can solve analytically, you can solve numerically. So I suggest you to solve numerically using 4th order Rangakutta and take a step size or grid size of 0.01 and plot the results. Plotting the results is also important. It will be helpful for your next homework problem. Thank you. That's all for this lecture, and I'll see you in next class.